All right, let's get started. So today we're finishing our first kind of piece of the tour of the very basics of supervised learning. We're going to talk about these family of models. It's called the exponential family of models. And why we care about these models, as we talked about, is they're going to allow us to generalize basically the kinds of models that we were using before to a wider range of error modes, okay, of different kinds of errors. And they'll also come back and play a starring role when we start to tackle unsupervised learning, where we don't have access to a target variable. And the underlying mechanics that we'll use here will set us up quite nicely for that. Just in terms of pacing, in terms of the course, what happens is I go away for a little while. Tengyu is going to come in and talk to you about a bunch of different things, kernels, SVMs, and deep learning. And then I'll come back to teach you a little bit about the unsupervised learning piece, which is, again, like a 2-week block where we kind of see kind of from first principles how those things work. And that area, I have to say, just as a plug for what's coming, that area is something that's been really exciting, kind of thrilling over the last couple of years, how much we can learn without labeled data or with really weak sources of data. That's been like a revolution in machine learning. So hopefully I can share some of that excitement with you. Okay. The thread is up, the lecture thread is up on Ed if you want to ask questions as usual, and everything's online before the lecture. I didn't put out a template today because I'm going to handwrite almost everything. So. All right, so what are we doing today? We're going to learn about these exponential family models, and they're basically going to be what you already know with slightly fancier notation. Basically, we've been ramping up the fancier notation each time and generalizing as appropriate how we want to go through them. We'll go do the definition and the motivation, and the definition at first will look like simultaneously like a little bit weird and like kind of like, oh, that doesn't really mean anything, it doesn't have any content, and then it will also look to you like it's impossible to satisfy, and that's kind of true, right? So these are fairly interesting objects we're going to be looking at, but they have a very nice kind of canonical form. Right? We'll then do a bunch of examples, a couple of different examples, and the notes here, the master notes here, are really good. I would definitely recommend going through them, the typed notes, just so you work through a couple of details. This is something that like you're going to get like a high level piece of how we go through it. Just do the calculations once and you will be convinced of like all the different claims that are in the lecture. If you try to reason about them without doing the calculations, it just makes your life more difficult than it needs to be. So just go through it once. It shouldn't take too long, but I'll give you kind of a high level tour today. So we'll do that definition of motivation. We'll do a couple of examples. And then last time we were talking about this question of how do we deal with multiple classes, right? Last time we were talking about binary classes, yes or no. Now if we want to have multiple classes out there, you want to know if there's a dog or a pig or a horse or whatever in there, this is called multiclass classification, and we'll talk a little bit about our friend softmax. What you'll really get out of this is that it will look kind of to you in the end like, oh, okay, that seems pretty reasonable. But you'll learn about some encoding that is fairly widespread called the one-hot encoding, which you would need practically if you were going to actually use any of these kind of things. I believe also your homework is out, but I don't quote me on that. I think it's out now, and I saw there were some questions ahead of class about that. Any other questions before we get started? Oh, please.
A logistical question in regards to the homework.
Oh yeah, I'm the wrong person. Yeah. But you're free to ask. Like, just tell you like I don't know.
I mean, those like service problems should be completed.
Oh yeah, don't ask that. Yeah. So we are blessed at Stanford with many great things. We have wonderful weather. We have like incredible faculty. We have the best students on the planet, and we're also blessed with great course support. And so I have no idea. All right. So let's see what's next. Okay. So the exponential family. Now I want to be clear, like I have mixed feelings about how I present this, because on one hand, I want to convey to you like the unbelievable historical significance of this and why you should know this kind of by rights of machine learning. On the other side, like there's an argument to be made that a lot of modern machine learning is not going to use this formulation and this framework, but if you start to read papers, it's canonical enough that it will come up in various different places, okay? So I don't want you thinking like, oh, this is all you can do when you model machine learning. This is like where the field is stopped. It's important historically. It is very nice to understand. It has a bunch of properties we care about, but it's not the state of the art, right? It's not what I go home and use exponential family models. It's weird that I go home and use any of these things, but I do, but it's not this one, okay? All right, so what we want to do is we want to have the following idea here, is that, and this is why it's so beautiful and will come back as a form that we want to think about, If P has a special form, which I'll show below, special form, then some questions come for free. Some, inference, learning come for free. Now, what do I mean by for free? I mean what you already know automatically applies to them. Okay? And when we start to worry about more complicated models, this will form like a subroutine that we'll use again and again. Like, oh, if we can reduce it to that form, then we're in good shape. That'll be the way we get to things like unsupervised learning. Okay. All right? Now, the form looks like this. Okay? Now, one thing I should highlight as I go through this. So this is the data, which you know. You already know this character. So the data are the labels. This thing is called the natural parameters. Okay? And I'll define the form in a second. The reason I want to highlight that is one place where you're likely to get kind of tripped up when we go through this is that there are kind of three sets of parameters, and I'll come back to that later. So if you're confused, there'll be natural parameters, canonical parameters, whatever. Doesn't matter. You'll see them all written down at one point, and that will kind of explain the mappings between them. But there are many different names for parameters in this lecture, and that's like the essence to understand it. And the reason that's important is the natural parameters, if you like, are so we can write this form, this functional form. B of y, exponential. This is where it gets the exponential name, eta. T of y minus a of eta. Okay. So I'm going to unpack this for a second, okay? Now, this form says basically my probability distribution factors, if you like, or can be written in this form. Not every probability distribution can, okay? The way you show that a probability distribution can be written in this form is you write it in this form. Okay? There's no secret shortcut here, right? You have to be able to express it as some linear thing in the parameters. So this is the parameters here, these natural parameters, times some t of y. I'll unpack that in 1 second, what t of y is. Minus this thing, which is the partition function, okay? So that's what it says. It says that your function, right? There are many functions that are in the world that could be probability densities. This one has this technical form, okay? We'll unpack this. Okay? This shouldn't be like obvious that these things are important or exist. So T of y is called the sufficient statistics. Sufficient statistics. Now, in this course, primarily, we'll use T of y equal to y. We won't kind of massage the data, but you can kind of think about T of y as capturing everything that's relevant to your data, right? These are the things that you're modeling that are in your data. And so in this example, like we're keeping everything. T of y being equal to y means just it's y itself, okay? Now, another thing people get confused about, this is necessarily the same dimension as eta, right? Why is that? Well, we take their dot product, okay? This is a dot product here. You can think about this. I'll write it above just so you clear also. You could write it like this if that's more clear to you. It's an inner product between the two, okay? So to take the inner product and for it to be meaningful, those have to be vectors of exactly the same dimension, okay? So if you want to have so many parameters, you have to have so many sufficient statistics, right? Okay, so far so good. B of y is called the base measure. It's not the most critical element here, but you need it, okay? The intellectual content of that is that B depends on y, but it does not depend on eta, okay? So it says basically, if you like, what's going on here is this term has all the interactions with y, this term has some interactions with eta, and the only way that eta and ty interact is through this term, okay? It's really a statement about how they interact. These functions are pretty powerful, right? Those are just arbitrary functions. But when they interact in a linear way. Sometimes these are generalized linear models, okay? All right, we'll keep staring at it. This character A is often called the log partition function. Now, this is a weird comment that I'm going to make, okay? And it does not depend on, well, its friend. It doesn't depend on y, just as I just said. It does not depend on y. Okay, now, this thing is picked effectively as a way of normalizing the distribution, so it's a probability. So it sums to 1. When I integrate it, or I sum up over the discrete values, all the y's, it's going to sum to 1. So that may make you think that A in some way is like not the star of the show. It's just this thing that kind of like adds up everything. But actually this log partition function contains almost all the information, it turns out, of the function. And that's a weird thing, but it's true, okay? So talk about that. So this contains A, and then you have this linear interaction term where the statistics interact with the data, okay? Now, just to make sure it's clear, y, a, and b are scalars, scalar functions. So a of eta, b of y are scalars, okay? Just to make sure the types are clear. And these two characters have the same dimension. Okay. So far, so good. All right, so let's highlight where all these characters are so you just see them visually, same, and y's. Okay, so far, so good. All right, now here's the crazy thing. Many of the distributions that you've encountered in your life, I don't know how often you encounter distributions, but if you encounter them at a relative frequency, a lot of them are of this form. And that was a huge win for statistics because they said all this stuff we're doing on distributions, a lot of it can be mapped into this, what looks like, as I said, a trivial statement, and at the same time seems also impossible that it would be there. So let's look at some examples and see how we map into this form. Probably you're thinking about, you are going through some distributions in your head. If you look at them and you're like, I'm not sure that it is of that form. So let's look at the simplest version of that and see that actually, yep, these things are of the form. So let's look at some examples. Okay. Before doing that example, I just want to, are there any questions about the content of this? And I'm happy to defer, so please feel free to ask a question and I can tell you to defer if there's something else. Clear enough? Yeah, please.
Where does X disappear? Because I guess like that now we were thinking of.
There's no X in this equation. Don't worry about X. It'll come back in a minute. Yeah, wonderful, wonderful point. Yeah, there's no X here. There's just a Y, which is your data. There's no X's and features, and they're going to make an appearance later. They will be one of these parameters. Yeah.
In a string. As little as a capital P, so are we talking about all the density where?
Yeah, it's a PDF.
Okay.
It's a PDF.
It says Y given A.
It's not given. Remember, it's our semicolon. Those are the parameters. Remember, there's a bar which says given, which is condition, and then there's a semicolon which says these are parameters. Yeah. See, these eta are the parameters of the model, right? And they're going to sweep up all that nasty notation that I talked about last time. Wonderful questions. Please.
And we said that T of Y is equal to Y. Does that mean T of Y is also a scalar?
In some of the examples that we'll see later, yes. Yeah. It doesn't need to be. Yeah. Just to make my life a little bit simpler in this class. It's not a requirement of the model. Yeah. Awesome. Wonderful questions. Okay. This is a requirement, just so we're clear. These have to have the same dimensions. Otherwise, it doesn't make sense. I'm not saying something deep. I'm just saying, like, otherwise, your brain should segfault. Like, what am I taking a thing and multiplying it by? Right? Okay. Right. Because this entire expression has to be a scalar for it to make sense. Okay, great. So let's take a look at an example. So probably the first example that you should think about, I would guess, are Bernoulli's, right? Bernoulli random variables. So what are these? So we're going to have some phi probability of an event, right? I guess the most common thing people use is like flipping a biased coin, right? For some probability that it's heads, some probability that it's tails, something like this. Okay. So here, when we've seen this before, phi, it had this form. Remember this form that we used? Maybe this looks a little bit familiar. 1 minus y, okay? So the probability of y, for 1 is phi, and when y is 1, it's this term. When y is 0, it's this term. Okay, just a compact way to write it. P and 1 minus p is all I'm writing here, if you think about kind of a heads-tails distribution. Okay. All right, so this is not obviously of the form. Let's go get the form. Let's go get our friend. From up above. How are we going to put it in this form? Okay, all right, and I will draw a box around it. All right? Now, when we do this, we're like, well, we got to get an x somewhere, right? I mean, that seems pretty natural. So we're gonna put an exp in there, and we're going to exp of y log phi plus 1 minus y log 1 minus phi. Okay, so far so good. We're making a little bit of progress. Well, the problem we have right now is the y's are interacting in two places, right? So what do we have to do? Well, we have to bring all the y's together because the y's and the phi's, the parameters, like they're not etas yet. Well, we'll give ourselves some freedom, but intuitively, like the parameters should all be looped, should all be somewhere together, okay? So what is that going to be? Phi 1 minus phi plus log 1 by phi. Now we seem to be in kind of the right situation because we have this character here, which kind of looks like the interaction terms, right? Y and the model parameters are interacting. And we have something here that's isolated that's just a function of the model parameters, okay? Now, it's going to turn out that phi is not going to be equal to eta, right? Because this thing here is not of the right functional form. So we got to figure that out. So what's our best guess for what this eta will be? Well, why not what it looks like? 1 minus phi, okay? So we want to set to show that it's of the right form, we postulate that this thing is actually equal to eta, okay? Now, that means this thing here has to be some function of eta, right? Now that seems, at one hand, kind of obvious, right? Because it only depends on phi, and that's a local transformation for phi, but we're going to solve for it explicitly if that kind of hand-waving implicit function theorem kind of argument bothers you, okay? Right? So here, our goal is we're going to take ty as, again, going to be equal to y. We're going to take eta that way, and we want to understand what is the value of a. And what we claim it is, right, a of eta, or of nu, is we claim that that's going to be minus log of 1 by phi. All right, let's check that claim, right? That shouldn't be hard. And so why does that work? Well, copy this guy. Oops. So this goes to, well, I just take e of both sides, 1 by phi. Then I move this thing across, right, so that I can do whatever I like. 1 minus phi equals phi. Then I want to make sure I get all the phi's on one side. So I get phi times e eta plus 1. And I'm off to the races, right? So now I have phi is equal to 1 plus e to the minus eta over 1. Okay? Now, this means, by the way, that log of 1 minus phi, well, that's going to be equal to, oh, sorry, did I screw that up? Let's make sure I didn't screw that up. I'm just going to redo this piece just to make sure because I didn't do it in my notes. So it's going to be, oh no, it's 1, I'm right, e to the phi. Okay, so now I take 1 minus this, right? So that's going to be equal log of, this is a lot of arithmetic to do in one sitting, but this is going to be log of 1 plus e to the eta. Okay. So far, so good. So why does that satisfy me? Because that's a function of eta, right? Now, as I said, it's kind of straightforward from here because these things are just functions of each other, but this is technically what we needed to do to show that these things are actually equal. And in fact, we're in good shape now, okay? So what am I saying? I'm saying like this seems trivial on one hand because you're like, well, I could just put in whatever I want, but you can't put in whatever you want. You have to first separate out the interaction between y and the form, and then you have to be able to pull out the term that depends only on nu here, the parameters. Does that make sense? Let's see another example, please.
So I guess it's fine to have eta in the form of function of the parameter and not necessarily the parameter itself.
Right. I mean, a is a function. Yeah. Right, that's just a function of a. Just this happens to be a different one. Okay. Now, here's what's weird. Okay, I don't know if I should really mention this, but you should look. This thing actually, remember I told you all the action was in there? You can kind of look at this encoding. This is the log partition function, so a log is what we expected. This 1 plus en thing, well, if you think about like the different weights on the spaces, this is actually encoding the fact that there's like a positive and a negative state. And try and think about why that might actually be the case. In fact, if we start to compute the derivative of this thing, it's actually the expected value of y. That turns out not to be an accident. Okay. All right. Okay, before we get into that, let's go down one more. Okay, so what did I hope that you got from this? It's a tedious thing to walk through. You should walk through these on your own. There are 3 examples. You should also walk through the logistic kinds of examples and the others. Basically, the whole thing is I want to make it super clear what this statement means. I don't expect anything here to be mind-blowing. I don't think like our use of fractions is going to, change your lives. I'm just saying that like this is the content of the statement clear, right? You give me a probability distribution in one form, I'm going to translate it into into a same functional form such that it has, satisfies these conditions. And then in that case, this eta is now what's called the natural parameters, okay? And you're typically not given the function in the natural parameters, right? And you're going to be responsible on homework and in other places to do this. And the reason why is if you can do this mapping, then a bunch of stuff gets easy. Inference gets easy, learning gets easy, because now it turns out that you can show, and we'll talk about it in a second, you can do gradient descent on these parameters and it's going to be concave. And that's wild that you can solve all of these models the same way, okay? So I just want to make sure that the functional form is clear, and the reason we're doing it is because it's going to simplify some stuff. Please.
T function to massage into that form or
Yeah, awesome. So could you use the T function to massage in the form? Now, in this class, if you find yourself doing that too aggressively, you've probably done something wrong, just as like a heads up, because we don't use it too much. But yeah, you could do that in T. If T were like expressed in some way, and you were only modeling a piece of it as a result of this and saying the probability distribution didn't depend on one part, like T was a projection, you could do that too. But this is pretty hard to get around. So I think you're thinking in exactly the right way, kind of like, how do I get around and break this? And basically what it's saying is your interactions are arbitrary and Y, arbitrary and nu, and the interactions between them occur in the exp, right? And they're linear. And once they have this linear interaction term, whatever the function T is, those sufficient statistics, that's what you're modeling up to. And some folks asked, and I answered some advanced questions on ED, which none of you are responsible to know, about deriving things like why is logistic regression calibrated in certain ways in data. Those features, those sufficient statistics, are what feed into those arguments. So up to these sufficient statistics, this is how well you do. So when you play the game of massaging it, you're either throwing away information or you're not, in which case, that's what we're going to do here. Yeah. So it's a modeling choice. You could do it. Nothing that prevents you. But it means something about what you're doing underneath the covers. Okay, this is awesome. So now you learn something, which again, hopefully seems sort of trivial. You're like, oh, I can take that distribution of like heads and tails and put it into this weird functional form. And that will be interesting because one thing you should test your understanding of is, can you now, given a bunch of samples from heads and tails, like estimate the underlying parameters, right? Computing derivatives here seems a little bit nasty, right? These are like phi's and y's that are up in things. It's like, it looks like a weird function. Once I put it in this form, all of a sudden like it's nice and convex and life is good. But I have to look at estimating this parameter, not the original one. Is that making sense? Please ask me a question if not. All right, we'll see one more example and we'll come back to it. This is the only important thing that from what we need to do now. Let's look at the Gaussian, example 2. We'll only do these 2 examples. Okay? This is the Gaussian with fixed variance. This one's really good. Because, remember what the probability of y is. It's going to look like, 1 over 2 pi exp, and there is a negative, y minus mu square over 2 sigma square. Okay? Let's make sigma square equal to 1, actually. Make my life a little easier. Okay? Just for no reason. Okay? Now, how do we get that in our favorite form? So let me go copy our favorite form. Seems to be pretty close, right? I mean, we're in pretty good shape. What do we need to do? Well, we have to factor it in some way. So this constant we can absorb anywhere. We don't care about that. But we have to somehow pull this thing apart. Okay, so how are we going to do that? So we're going to put the 1 over 2 pi, square root of 2 pi here. And then we're going to pull out the e minus y squared over 2. Okay, so I'm just going to factor this, right? This is going to be minus y squared plus mu squared minus 2 mu y over 1/2. That's what this term is going to be, right? It's just straight multiplication. So I factor out the ey squared. What does that leave me with? Leaves me with x of this character, mu y minus 1/2 mu squared. Oops. Minus 1/2 mu squared. Okay, so what are our natural parameters? Well, eta is mu, which is why I accidentally wrote it right at the beginning, which would have been a little bit weird to do. T of y and a of n equals 1/2 eta squared. Ooh, mu squared. Okay? Whoa. Oh, yeah. Okay? Right? So because this is mu. Now, again, notice I differentiate this thing. What's the expected value of this character? Well, it's mu, right? But when I differentiate ay, I get exactly back mu, which is kind of interesting. This is trivial here. In the last example, it was non-trivial. It was like a weird function that I differentiated and I got back the actual probability distribution, right? Which is kind of bizarre that I would get that back. Okay? By the way, if that's not clear, differentiate this function with respect to eta and then see what you get. Okay? Does that make sense? Okay, so just to make sure we're verifying everything. Yep, this looks right. This is my b term. Oh, sorry. This is my b term. I'll highlight in different colors. So this is by. And this thing is the log partition function. Okay? And what I'm just trying to highlight is like this thing contains like a lot of information about the distribution in both of the examples we've seen. Please.
Distribution as one parameter?
No, it's a wonderful question. So right now we're worried about the case where y is going to be a scalar, which makes our lives a little bit easier. And so we're going to look at that. But you just have to have that the ty and n and eta actually resolve to a scalar, that they're the same type. So if your y has multiple dimensions, then you need more natural parameters. And that's actually pretty important because that's why they're, and why we call them natural. Like it's like your problem has, dimension d, then you need d free parameters. There is not, no. The thing is I wanted to have sigma squared be fixed, like I didn't want it to change per data point. That was important, and so it was easier to just write one there. If you put sigma squared in here and it was just a constant, then you would just push it into the appropriate spots and be done. They would just fold into this. If sigma squared were something that we're changing per data point, right? Like you were trying to estimate for every data point, not only its mean, but its possible variance. Like I give you a temperature reading and I say like, from all the data I've seen, I think it's 30 degrees. But I know that I haven't seen enough data, so I'm like plus or minus 2 degrees. If I've seen tons of data and I'm very confident, I'll say plus or minus 0.1 degrees, right? That is an estimation where sigma is part of the model, and then you would have another free parameter for it. Great question, and try and write that out. I don't know if that example is written out in the notes. If you get stuck or whatever, please send me a note. I'll write it up for you on Ed. Does that make sense? That capture your question? Yeah. Awesome. Okay. Yeah, awesome. So 2 questions on the live thread. The examples to go through on your own are the ones in the typed written notes, which contain these and one more, but just go through them on your own. Like I'll just wax poetic for 1 minute. If you haven't studied for a mathematically minded course, the way that I always did it, I still actually read textbooks and course notes and everything else is, I read them, I watch the lecture, whatever it is, then I try and remember those key spots and I try to derive them myself. It's the fastest way to figure out what didn't stick. So if you're like, oh, I can write the derivative in 2 minutes and you walk away, well, okay, you know everything for the lecture. If you get stuck, it's a really good signal that you don't do it. If you don't do it, and then that builds over time, something that you thought was trivial and you didn't actually put the time into, will end up biting you, right? Just lesson that I learned from too many years at a university. Why is the derivative equal to the expected value? I'm not going to prove that. I will just assert it here. I just want to show that, I just want you to observe that in both cases it's true. It's a wonderful question. Okay. It just takes a little bit of arithmetic to show. It's a wonderful question. Yeah. All right. Okay, so I'm gonna put those assertions in here now. So why do we care about this form? The first is what we said, inference is easy. Okay. the expected value of y given eta is the partial derivative with respect to the natural parameters of a of n. Okay? I would encourage you to compute this on all the examples. Okay? You don't want to, proving the general thing just takes a little bit of extra thing, but on all the examples so far you've seen, it's clearly true. And then why that's true in general is because it's the log of the sum of all the possible outcomes. Proving it for continuous stuff takes a little bit more effort. Okay, so don't worry about it there. Okay? But we've seen this is true. Okay? And this pattern holds. The variance is also the second derivative of an. Okay? Now, this pattern you may think holds. Like, oh, the third power is good. No, it doesn't work that way. Okay? Just these first two. That's the only ones that matter. Okay? These are the only ones that work. Okay? So why is this so interesting to me? One, because once you take your distribution, whatever the crazy distribution is, however wild it is, and distributions can get pretty insane, there's uncountably many of them, you put them into this form, you basically have a mechanical procedure to do inference and to do variance estimation, inference more important to us, but that also means that you can do learning. Right? And in fact, learning is well defined. Okay? In particular, this function is going to be concave in eta. Okay, hold on, let me write it this way. The MLE, remember we did the maximum likelihood estimator for all those things previously? Is concave. Okay? Please. That helps. Yeah, so that is definitely a piece of it. You have to do one extra step, but you're exactly on the right thing. That's exactly how you can go improve it. Just compute it directly, right, and see that it's positive in the way that you think. If the second derivative is positive everywhere, then it's convex. But yeah, so you have to. There's a negative in front, but that's a small issue. Wonderful, yeah. Exactly right. That's if you remember last time, the way we framed all of our estimation problems was take the log likelihood that was there, L of theta, and then use gradient descent on that. And this is basically saying that the resulting formulation, if I use the natural parameter, is always guaranteed to be concave. Please?
So why is the absolute value of y is not?
Yeah, so the thing is you can compute this directly by looking at exactly when you compute the derivative and pull it out. The way that you do it, I'm not going to prove it in class, but I'll just tell you, like, it's not a mysterious statement. What you do is you look at all of the, for the discrete case, you look at the fact that it's a log partition, means it's a sum over all the possible worlds, meaning all the possible ways that y could be assigned, right? So there's going to be a term in there for each one of them because it sums over all of them. That's what it does. So maybe this is getting way too abstract and mysterious. Maybe it's just better to prove. So if I look here, look at this part of the distribution, this may not sum to 1, right? If I just started to do it. So like if I took and summed over y, oops. If I sum y of this expression, let's call this gy, it may not equal 1. It's not guaranteed to be equal to 1, okay? Because it's just some collection of values and some other stuff. This thing is the function, this eta here, makes sure that it's equal to 1. So it's the scalar, as we were talking about before, that makes sure whatever this sums to, it's going to divide over it. So it's sometimes written as 1 over z, the partition function. However, that means that the way you get it, one derivation of it is, you sum over all the different values. So it is like the sum of everything over 1 is actually what, so this character has to be equal to this. Right? Because it has to cancel out. It has to be actually equal to 1 when I compute it. And that means that it's basically of the form a sum over all the possible values of y. And so if you compute the derivative inside, when you take the log of that, each one of the y's is going to come down next to exactly this functional form. Okay? All right? So if that's too mysterious, I didn't want to prove it because it gets like strange, but I'm happy to write out the proof. It's super straightforward. Okay. Awesome. So all I care about is the thing that I'm trying to get across, because I'm trying to give you a guided tour, I don't want to get too, I want to do enough details that you see all the pieces so you can go back and understand how they work, but I don't want to get bogged down in things that I don't think are like super critical for you to understand. And also I don't want to do things that I think you should do on your own because doing them mechanically will teach you better than me like inscrutably writing for the 100th time how to prove this. But if I'm wrong and you want to watch me inscrutably write, I don't know, you can log into a Twitch stream or something. Awesome. All right, all good. Okay, so clear enough like why we did this? So barring these assertions, if you get your probability distribution into this form, then all of a sudden you get inference and learning and a bunch of other stuff for free. However, one of the things is, as was correctly pointed out, there was a little bit of a bait and switch here. We started last time to think about various different models and how we put those models inside. So where did the data in X go? And that's what we actually need to figure out here. Okay? All right, so let's talk about generalized linear models. Okay, so the point that I really want you to get across is these are all design assumptions, okay? So these are all design choices that you can actually make in your model, and we'll get to them and talk about what you want to do, okay? And you can also think about them as assumptions. All right, so first, what we're going to say is we're going to claim that the distribution of our label given X for some parameters theta follows an exponential family, okay? Now, I claim without much justification here that this is an important family. Now you can say it's an important family because, as we'll talk about, many different data types like fall into this that you've seen. So if you look at binary things, you want to do Y as binary, well that's Bernoulli, right? So we looked at that classification. If you want to have real valued Y's, well we have a couple of them that we could use, but we saw Gaussians, okay? If you want to do counts, like you're actually counting, like how many people walk by a particular thing, or how many packets arrive at a server, something like that, then that's a different distribution. It's called Poisson, okay? If it's, you want all the whole real line, right? You want real positive line. Well, there's two different fancy distributions there called gamma, right? You don't need to know these per se, but what I'm trying to explain to you, kind of proof by writing a lot and gesturing wildly, is that these, exponential. Laplacian's also in this. If you want distributions, just one more, then this is called the Dirichlet distribution. Dirichlet. So what am I trying to get across here? These are probably most of the distributions you've heard of. There are more that I'm not writing down, but they all fall into this exponential family. Now, one hypothesis is that we figured out this technology and that's why we described distributions this way, but that's actually not true. We went the other way around. We were doing things ad hoc for each one of them, and this tied them up and put them nicely together. Okay? So you pick your error mode. And the way you pick the error mode is it has to have the right type. If you're observing binary data, you want to use a Bernoulli, right? Or something that has a binary type. If you're observing real data, you want to use a Gaussian, counts, Poisson, so on. Okay? So there's a data type mapping here, right? The second thing that you have is that your natural parameters, and this is where they come back in, are going to be of this following form. With theta, element of RD plus 1, and X, also element of RD plus 1. Okay? So here, we're going to make the assumption that after, subject to noise, our model varies linearly with some underlying features. Okay? Now you're going to see later, there's actually a more powerful assumption than you realize. If you take your model to be very, very large and have a huge number of features, almost everything becomes linear in that space. High dimensional geometry is very, very weird. So it's not like if you think in low dimensions, you're like, oh, there's only so many lines I can draw. I can't separate out my data. If you take your data and put it up into a huge dimensional space, odds are it will be linearly separable. There'll be a line through it. We'll come back to that. Okay? So this is just the thing there. And then 3, once you've made that assumption, your inference is super easy. Right? At test time, you output E of y given x and theta. Okay? I said another way, h of theta of x equals E of y given x. Okay, so hopefully this makes sense, okay? So I'll walk through exactly what's going to happen in 1 second just to make sure it's clear, but this means that we're doing this prediction. And one thing that we sneaked past you was that when we went to logistic regression, all of a sudden we started with these hypotheses where instead of returning like yes or no, we just returned a probability distribution over it, Okay, and that was a change, right? When we were doing regression, we returned just a value. Here we're just returning actually like your probability that you think y has a particular value. That's what you do for inference. That's how inference is defined. Okay, so let me make sure this is super clear how this works. Your data comes in as x. It then goes into your linear model. You compute phi transpose x with your parameters. This is your box. You get out eta, right? Theta t becomes eta in the parameter you have before. You feed that to your exponential model. X model does whatever it does. There's b's and t's and whatever in there, but now you know your value for eta. Nu, whatever you want. I'm using both. And then if you want to train, you do max over phi of log py x phi. If you want to do inference, you do ey x phi. Okay? This is learning. This is inference. Okay? So all you pick here is you pick your data, you pick the features, and then you run this procedure, and everything's kind of automated for you. In the sense that, like, in the sense that you now know a general recipe to do maximum likelihood estimation and do inference. And it's not obvious how to do that, by the way. There are scenarios where we don't know how to do maximum likelihood estimation. So right now, like your universe is like, oh, everything you've shown me, you've done maximum likelihood estimation. It's been really easy. I'm like, yeah, that's fair. But there's a big world out there of stuff that is hard to cram into this. And so what this says is if you can put it into this form, maximum likelihood estimation and inference becomes super, super easy. Okay? And learning here has a nice form. Theta j looks like this. And you can directly check this. Plus alpha yi minus h theta of xi. xji. So why is that the case? Well, we saw that it was the case in all the other models. You just have to go through and compute the derivative and convince yourself. But now that it's in this form, just computing the derivatives with respect to theta as you go through here, because it occurs only in this theta tx, we'll get that out. So one of the reasons I was delaying proving it in the special cases is because you have to do all of these transformations to put it into the right nice form. And then when I compute the derivative, my life gets really, really easy. If you compute it in the natural parameters, it looks weird. But if you compute it in the original parameters, it looks weird. But if you compute it this way, life is pretty good, okay? And this, by the way, here is always this thing, right? Always a hypothesis. Okay. So far, so good? Please.
I want to ask, like, is this kind of different from what we did originally? Originally, if I'm not wrong, we were just doing a linear model, now we're adding an exponential layer.
Yeah, so it's a great question. Let me do one more example, and then hopefully that will become clear about how they relate. So let me just run through logistic regression then. I think that'll probably maybe answer that question. So it'll show exactly how they fit together. Terminology, okay? So there's the model parameter. This is phi. There's the natural parameter, which in a linear model, we always substitute a generalized linear model. We always substitute. So this was the eta before. And then there's the canonical parameters. Okay? So these were like phi for Bernoulli. Okay? Or mu and sigma square for Gaussians. Okay? And this G here, we're going to call the canonical response in this G inverse. So G is called the canonical response. Okay, so why do I do this? I want to make sure it's really clear what all the pieces are and what's going on here. There's some model parameters. That's the thing that we're going to solve with respect to. That's the thing that we're going to do gradient descent on. That's the thing that we're going to do the h theta with respect to. Theta is then dotted into the model or the data. That's what this x is. This is data right here. That becomes the natural parameter, which then goes to the exponential model now tells you how to operate on. Okay, and then I can do everything I want on the natural parameter. That's what tells me the distribution. And so in the case we're doing logistic regression, which we'll talk about in 1 second, you have a linear thing, and then your errors are of the form, I make an error, that I sometimes switch the class, if you like. I get the wrong answer with some probability. And then there's this link, which are these canonical parameters. And this is the content of what we're talking about here is you write them down in these canonical parameters, and then they have people write them down in whatever messy form we found them. And I'm asserting that a lot of them can be put into that nice exponential form through what's called this canonical response function or its link function. And that allows us to treat them in the same way. So this is super important because when you encounter one of these distributions, you probably encounter it in this form. You have to put it into this form, and then that lets you do everything that we just talked about in one clean way. Learning becomes this nice simple rule. Inference becomes this nice simple rule. Okay. Awesome. All right. Okay. So let's look at logistic regression, just so it's super clear what that means. All right. So h theta of x. Well, we said it's the expected value of y given x and some parameters theta. Okay. This theta, right? So we have, right? So there's theta equals 1 plus 1 eta minus n, and then the model 1 over 1 plus theta. Oops. E to the minus theta tx. Okay. So this piece here, theta was theta should be driven. Sorry, this was our model parameter. This was after we transformed to the natural parameters, that's this character, and this is what we wrote down last time. So when we went to do logistic regression, remember we had a loss function that looked like this. This was our sigmoid or logistic function. And then what I'm saying is that we, right now, to get the derivatives and do everything else, which I skated on last time, I now no longer have to skate on because I just made it more abstract. I transform it into this parameter space, then I'm good. Okay? So in one hand, as I said, it's totally trivial. I'm just doing a transformation of how I represent the numbers, but it also seems weird that I can do this, and I'm asserting that in these cases I can, and that's what allows us to go and treat all those different distributions in some way. So if I give you some features, you dot forward, you learn a model, and then you have an error, like I'm looking at counts, I'm observing them. Counts have a very different distribution than the errors I would expect on 0, 1 things, or the errors I would expect on a linear regression. I just plug that model in, that natural model in, and out falls a pretty reasonable class of machine learning models, okay? And you may say, the thing that people usually react to is they say something like, well, what if I want to do something that's more complicated than linear? But linear is pretty powerful. I can take my features and square them. I can multiply them together. It's still linear, right? I can take my feature 5 could be the product of the preceding 7. And so this turns out to be a wildly popular class of machine learning models. In fact, there are entire books that are written about generalized linear models. And there's a citation to McCullough, which is the standard reference. I'm not sure I advise necessarily reading it, but it's the standard reference. Not because it's not a great book, just like, it's long. Okay, please.
Do you think that there will be more improvements in the theory of machine learning such that quadratic and other models are more applicable and useful? Because I think right now linear is extremely powerful and it doesn't make a lot of sense.
Yeah. Man, I really feel like I should buy you something. So that's a great question. So there's a lot of folks that have done through the years, as we'll talk about when you get to kernels, things like polynomial kernels and exponential kernels, and those are very powerful ways to model the world. What I was kind of hinting at before is the linear model has this sneaky out in the back, which is you get to pick the features. So if you know up front that that the squares of the temperatures are more indicative than the raw values, you can just put that into your model and learn more and more features. And so it's not a question of eventually we're going to get powerful and use those features. We can use them today. The crazy thing is we can reduce a lot of the things you would naturally do to this model. And you'll see eventually, someone was asking about these infinite dimensional feature models. Those are what kernels are. You can reduce those to linear in an infinite dimensional space. So it's wildly important there to do this. The other bit, which is also my personal opinion on these things, one of the things that has really bitten me again and again is that simple, stupid things work extraordinarily well with a given enough data. And in fact, the trend has been larger and larger amounts of data for the last 40 years. And every time we think it's going to run out of gas and get fancy, a bunch of fancy people, academics, start writing papers about clever ways to do X, Y, or Z. And usually they get smoked by more data and linear stuff. And there's a great paper about this that I can post of different eras of machine learning when this happened. And the thing that's remarkable about modern machine learning to me is not how sophisticated it is, but how we basically do the same thing and just pour in mountains of data. Right now there's a particular model that's very hot. In 5 years, will it be hot? I don't know. right? Maybe 5 years ago it wasn't. I guess 5 years ago was kind of hot, but and then a new one will come. But the pattern of like we just dump in all this information and just optimize the crap out of these parameters, like that works really well. So the thing that I'm trying to get across there is, as you said, is like the future of machine learning seems to me to be more tied with like understanding relatively simple applications when we have huge amounts of data underneath the covers. Yeah. But I'm a zealot there. I taught the large language model course with Tatsu last quarter, so I'm a believer. You can think it's nonsense. It's a personal opinion, but wonderful question. Yeah, awesome. Others? All right. So again, same thing. I'll do Gaussian just to stall to make sure this is clear, because I hope if I'm very optimistic, you're like, oh, this is obvious. There's no content here. I understand it perfectly. If we are in that universe, like I will be extremely happy. If you're like baffled, please ask me a question. This is the same. This is a Gaussian. How do I do prediction? Well, when I have something, I pick the mean value that I would have. That's exactly the same piece that's here. How do I do the estimation? Well, that's exactly theta tx. That's what we were doing before when we fit a line. Okay? Same thing. Okay. So all I'm saying is what we've done so far in the first K lectures, we've now compressed to basically one equation, one schema of this thing. We now know how to do inference and we know how to do learning. And maybe it's tough to appreciate in the sense that you're like, well, I didn't encounter 1,000 models before, but now all of these different models can be shoehorned into this. And that's quite powerful. And we'll use that quite a bit later when we do, much more kind of advanced stuff. All right, awesome. If there are no questions, I'm going to move on to multiclass. All right, so the last thing I want to describe here, which is important for you, and I think you have to use in your homework, is how we deal with multiclass classification. And I should say, the trend has been in machine learning, not only these big models that I was just excited and ranting about, which you can take or leave, but is that you train models on a variety of tasks, more broad than even a variety of classes. You train them to do many things at once. In fact, weirdly, as I may have told you, the thing that we seem to be doing as a field right now is training a model to do something, task A, and then using it for task B. And weirdly, that makes the model more robust. So the typical task that we do there, by the way, is predicting the next word, which seems like a really basic task. You look at a sentence and you you view the words as individually. This is oversimplified, but how it works. Every token is a class, right? So is the word cat, dog, whatever. You just take a vocabulary of 50,000 words, let's say, and then you predict which one do you think is likely to be in the next space. So I read the first part of the sentence and I predict. This turns the entire web into a training corpus, right? Because now any piece of text I can evaluate in a multi-class way. We train it just to do that, and weird behavior emerges. Like it can write pieces of code for you. It can answer questions in narrative form. And only when we train it on lots and lots and lots of data. And it's a little bit spooky. So anyway, so this is what multiclass is for. And this is actually, something that we use every day. Awesome, wonderful question. What is the disconnect between the power of linear models and the need for nonlinear components in a neural net? Wonderful question. So right now what we've done is we've said, and the exchange was wonderful, hey, what about more powerful feature representations? What neural nets basically are and why they're so amazing is, and they take your data, if you like, and they pick out what those features are, what those X's should be from the underlying data. And then usually on the end, you just have a linear model. That's, there's little tweaks and variations, but that's pretty much what you have. So the question of where does the X come from? You give me an image of a cat. How do I get good features about images? That's what the neural net is actually solving. And that's where we need nonlinearity. But it comes in at that piece, not at the prediction piece. Great questions. All right, so here we're going to look at discrete values. If you're familiar with distributions up to some fixed k, so we have cat, dog, car, I don't know, whatever else. Oh, I wanted one other one. Oh, bus. Okay. So here k is 4. All right, so I want to predict among that set. It's kind of weird. I promise you that you're only going to see a cat, a dog, a car, a bus. You could ask, well, what if I show it a horse? It doesn't have to predict anything. It can predict whatever it wants in that situation, right? But for this case, imagine that I'm just distinguishing among those 4 classes. Or the crazy example I gave you where your classes are every word in, say, the English language. Okay. All right. How do you encode this? It's encoded as a one-hot vector. It's called a one-hot vector, right? And the distribution, the error distribution, that is the thing that we just talked about, to the k. Okay? So such that, sum y equals 1 to the k equals 1. Okay? So there's a vector that's in 0, 1, but it's precisely one thing is lit up. So for example, you could have, the cat one is 1, 0, 0, 0. This could be cat. 0, 1, 0, 0. This could represent dog. You get the pattern 0, 0, 1, 0. This could represent car, and so on. Okay? So those vectors, basically these one-hot vectors, they seem pretty wasteful, but you don't have to store all the zeros. It's not as bad as it looks. But like this is how you intuitively think, mathematically think about how the data looks. Okay? Clear enough? So we reduced our problem from dealing with these categorical labels to dealing with vectors. Now, let's try to classify them. All right, so let's draw a quick picture, okay? Oops. So let's imagine our data looks like this. So there are some class 1s, which I guess are cats here. There are some buses here, which are 4s. There are some dogs here. So I'm just drawing all nice and clustered. Of course, your data never really looks like this, but that's okay. All right, so what do I want in this situation? Okay, I want lines. So this is corresponding to one class. As I said, this is the cat class. This is the dog class. Oops. So on. Okay. So how does this multi-class thing work? Oh, that's too close. The colors don't really matter, but I started, so now I'm going to finish. All right. Car, bus. Okay, so what do I want here? What I need to do is I want to pick, because we're looking at linear separators for this, I kind of want to look at, what I'll do is I'll pick a line that, for example, separates the cats from everything else. Okay, so this will be theta 1 dot x is equal to 0. So this is the line I'm drawing here. So I want to pick theta, right? So that on one side are the cats, and on the other side is everything else. Does that intuitively make sense? Right? For theta 2, for theta 4, what would I like to do? Well, I'd also like to pick something where, here. Oops. Theta 4 dot x equals 0. So I like it so that, again, the buses are on one side and everything else is there. Now, if you look at this geometrically, it becomes pretty clear, by the way. Like, there's lots of choices, right? I could have picked here, I could have picked there. Right? What we will try and prefer, sometimes called max margin, we actually prefer that it's kind of as far away from the two data points as possible. It's like as close to in the middle as possible. And you can verify that it actually makes sense, and you can verify that that's actually what you'll hope will happen. You get something like this. All right? This is the x3. So in this case, by the way, which is really nice, everything is nice and linear separable, right? This side has the dogs on it, this side has the cars on it, and so on. Okay? So there's one line that explains, that kind of can separate each one of them. Now the question is, how do you pick? Right? So the way you do it, right, is when you get a point, you're going to compute its value against each one of them. Theta 1, theta 2, theta 3. I'm just going to draw the first ones. First three, theta 4, whatever. Okay? And these are going to give me some values. Okay? And the values are going to be basically, you can think about as like, kind of how close are they to the various lines. Okay? It's a dot product. Yeah, please. I'm just saying, like, this is the line where on this side, theta is going to be, so for this side, theta is going to be positive, and on this side, it's going to be negative all over here. Right? And so I'm just drawing like the deciding line. So as you're more cat-like, you're getting a higher score from this. You're getting something that's like, a larger score. As you're here, you're getting a negative cat score. Okay? Right? So the point is each one of these things, because of that, is going to give you, great question, is going to give you some score. So maybe it's a cat, so it looks like, this thing, 0.1, and everybody else is like, yeah, I'm not really sure. Maybe I'm kind of like borderline about all the other classes. This is what you would hope would happen, okay? Each model gives me a score. And then, did you have a question?
Yes, a quick question about the center. So what happens if you were in the center?
Yeah, great question. So right now, remember, like you give me a horse and you put the horse in the center. Oof, who knows, right? Who knows what I'll get? I will be able to run this procedure and it will get confused. So one of the things that happens in neural nets, by the way, is that they're in large scale models is when you're really high dimensional, right? And you have a bunch of these lines and other things, there will be pockets that are actually nowhere close to anything. But now look, it's totally well defined. This character here has a normal this way. This one will get a negative score from everybody, right? Now you could look and say if it gets a negative score from every single thing, maybe I should be suspicious of it. But that's not in general something that will happen. One of these, unfortunately, will be higher than the others. Like if it's here, it may be closer to cat. And so it says, oh, it's a cat that was near the border or something like that. And it will pick. But let's get to the procedure first before talking about the exceptions. Okay? So we have all of these. Then what happens? We exponentiate them, right? 0.7 minus 0.5, 0.1, so on. And then this actually leads to probabilities. Right? Actually, let's make this really negative. This is like minus 10, either minus 10. Then these things are approximately like, 2.1, whatever, so on. I get the values out, and then I normalize them by summing all of them. So I sum all these together. So I sum all these characters, sum theta I dot x, and that gives me some value z. And I divide this number by z, divide this number by z, and that's going to give me a number between 0 and 1 because I sum them up and they're all positive. So 0.5, 0.17, so on. 2.50. Okay? The point is I compute this exponential, I sum, oops, this should be e of this thing, and then that is my normalizing term. I sum it up. So let me write it in a cleaner form. It's the following thing. So the probability of y equals to x, probability of y equal to k is, given x and theta, has the following form. It's exp of theta k dot x over sum k, sum j, sorry, exp theta j dot x. Okay? J goes from 1 to k. Okay? I just described the procedure in elaborate detail here, but this is basically what's going on. Okay? This is exactly what's going on. It's not basically. Please.
So why it's an exponential rather than the topic?
Okay, so two things. One is, this makes sure that everything is, so exactly as we were talking about before, these are each, think about these as each like a logistic regression model. So in the logistic regression model, you take this and get the natural parameter, then you exponentiate it. If you had an offset, like if you had some function there, you would still need, just as we did in the exponential model, you need to sum to make it a probability distribution. So that's where the z comes up. So the exp is because we're doing these general linear models, and that gives us the nice kind of functional form that we wanted underneath the covers that we've been using in all our predictive problems for in the class or not. Think about logistic regression, binary or not. And then we have many different scores, and then the procedure is just to normalize them. Okay? And this kind of makes sense, right? It's like, this is saying like how strong a classification I am, right? If these cats, like if there's a cat way over here, maybe this is a super cat, like the clearest picture of a cat you've ever seen. In that case, like it should get a really high score and you should be really confident in it. That's the intuition. Now, is that always true? No, certainly not. A picture of a horse could show up over here. We hope it doesn't. But mechanically, is this clear what happens? All right. Please.
That's what I asked this to you when you said that ultimately we will have to do one versus all classification for each of these classes. So I think that's true here too. Right?
Yeah, this is.
That.
Yeah, so exactly. So this is basically a compact form of what we call one versus all, which says like, okay, how confident is my cat detector? How confident is my dog detector? How confident is my whatever this is, car detector? I don't know what that is. Yeah, car detector. Does that make sense? Yeah. And so you just bake off their relative strengths. That's how you do multi-class classification at once. Cool. All right, so how do you train this? Well, what you're given is you're given something that looks like this. say 1, 2, 3, put 4 in there. You're told it's a cat, you have probability 1 here, and you have 0 everywhere else. This is what you're actually given. That's what the label looks like, okay? Your probability, your p hat, your estimate, will not look like that. It will actually look like, oh, I'm pretty confident it's a cat, but I have little pieces at each one of the others. 1, 2, 3, 4, okay? Maybe some spike, okay? This is at inference time. What I'm trying to get across is, when you actually look at these things, they will give you small probabilities that it's everywhere because it's doing this normalization. Okay? Now, one thing that people do, by the way, is something they call label smoothing. They take this and they push a small amount of mass everywhere else, right? So you take the 1 and you kind of say like, oh, I'm going to put a small, tiny amount of mass everywhere else. And that's basically to account for the fact that your labels are often wrong. Right? You contain, even very popular, well-studied benchmarks will have, 3% of their labels be wrong or something. So you can imagine how you would kind of smooth and why that would be bad when you're training a system. If you're like, it's definitely not a cat, you're like, no, there's a small possibility it's a cat. I should admit that possibility. That's a very different statement if you imagine those two. Okay, awesome. So what happens here? Well, the great thing is like, this follows exactly what we've been doing the whole time. So we now introduce this is also sometimes a cross entropy term, right? Which is equal to this guy. But this follows our basic recipe, which is, so py equals k times log of p hat of y. This equals minus log py hat of yi, okay? So this is the ground truth label. Okay, so this is in case we don't do smoothing. Basically, our loss to minimize the cross entropy is the same as minimizing the log of our expected probability. And that thing has a very fancy name. That's a logit. And that's you'll see these negative log likelihood things all over machine learning packages. That's what they're doing, okay? And this equals, just so we're super clear, it equals minus log of exp theta I dot x over sum exp theta j dot x. J goes from 1 to k, okay? And this is what we minimize. And that's it. And so how do you solve this model? Just run gradient descent. All right. That's it. All right. Any questions about this?
What part of that is the logit again? What's the definition?
Oh, the logit is a log probability. Great question. So this is the terminology for a log probability. So this thing comes up, the reason I call that is you'll probably encounter that term. I just wanted you to be familiar with it. And you don't usually predict, you don't actually write out the probability functions. You don't take the exp. You actually just take the log of those probabilities, and that's what you actually minimize. And so you will use them, and they're in log scale. So you'll often see like machine learning code spit out these like, -7, -4, 3.21. That's what they are, they're logits. And you'll see that term logit everywhere. Yes, please.
Why is there a negative sign?
Because otherwise it would be a maximization. Yeah, it's just to make the function sign so that we have a minimization. Wonderful question. Yeah, please.
So that's the thing that you're minimizing?
Yeah.
The thing is, it doesn't look like it has any dependence on the label though. So.
Awesome question. What a wonderful question. Yeah, it's hidden right here. This theta I, this I is the ground truth I, right? That's what this statement is. This is the ground truth. Wonderful.
So that's not your parameters.
No, it's just like you picked out that one, and then you get your loss function kind of like perfectly encodes it. If you put in the label smoothing, then in fact it's not just one theta I that's there. They each get a weighting associated with them as well. But here, that was the trick. This yi is the same as the actual ground truth. Wonderful, wonderful question. Please.
I have a question
Sure.
Like when you assign the score, should have actually been the sigmoid function that assign the score, right? Not only the theta x.
Yeah, great question. Yeah. So here it's the theta x, and then I'm taking the exponential, but you would also have like an exp1 over x thing. Yeah. But here, For this model, I don't do that. So what you're saying is an alternate model where you take all of the logistic regressions and you just say like, what's the probability of each one, and then you compare them. And I'm saying, no, you do it in terms of the logits here, and this is how you bake them off all at the same time. The difference between them is not super critical, but this is the one we use. But it's a great point that they're different. So I did kind of, by sleight of hand here, I said, oh, this is like you're doing a logistic regression. But this, again, is like saying, so if you think about logistic regression as there's a yes class and a no class. In the yes class, I have the weight is x above theta t the x. This is each saying that this is the weight of every one of those possible worlds, and then I'm summing over all of them. And so that's why this is consistent with logistic regression. Imagine a null world that occurred here that said it's either the class 1 or it's none of the classes. And so its feature, I'm just going to default to 1 because I don't care. It could be any scalar. Then that gets you exactly back to logistic regression. Does that make the connection clear? Yeah, so they really are the same. I just derive them in a slightly different way. Wonderful question. Please.
About the loss function, we just go down to that.
Sure.
So is this concept of the loss function be something we've seen before as a manipulation of that, or is this a new one?
Yeah, so if you've seen, so this is a new function, I guess for us potentially. We have seen it because of the discussion we just had in another guy's. It actually is the binary cross entropy is the logistic function. And so this is a generalization of that. And if you've ever seen entropy or cross entropy, which I think, it doesn't matter if you've seen it or not. This is it, right? It's just a functional form that we care about. It's a kind of a distance between probability distributions. Yeah. I care, the reason I say this is not because I think there's something mystical here. So if you haven't seen entropy before, I guess this would be mysterious. And potentially even if you have seen entropy before, because entropy is a mysterious thing, but this is the loss function that you use. And it's the reason you use it is because it generalizes in the way we just talked about. I don't think you need to know any of that, but it's fine. Please.
Just to clarify, so where you have the clusters, so the x are just x and y, right?
There's no y in this diagram, but yeah.
So what are the x?
So this here, x is a two-dimensional vector. So this is a little bit of a weird plot, right? X is cat is a two-dimensional vector because I only have 2 dimensions to draw on, and so I put them there. And that's why this picture looks a little bit different than maybe you're thinking about it as like a function or a curve or something. But that's the difference.
So technically quite many features with the higher dimensions, but it's...
Exactly right. So in higher dimensions, what you would expect is rather than lines, which are one-dimensional, you'd expect, d minus one-dimensional big planes that were separating everything out, hyperplanes. And then they would live on one side or the other, and you would care about the distance effectively there. And so I'm drawing like the contour representation of the function, right? Yeah, awesome question. And then there's the y's are encoded, as we were just discussing, by which index I use, right? Please.
For image recognition, you normally work in Euclidean space or some different transformation like PCA or...
Oh, awesome question. Yeah, so we'll talk about PCA when I come back to join you and why we use that. PCA is a method. So the two things PCA fix for you is if you have x's that have different scales or have different meanings, like, if all your temperatures are between 80 and 82 degrees, but they're really significant, PCA is a way of centering and whitening your data, meaning like subtracting off the mean and standardizing and normalizing that. And so that's a technique that is very, very commonly used in statistical analysis. And so we'll talk about that and how to provably find that and what its justifications for here. When you're doing things like image analysis, actually the methods have been more toward raw features and raw pixels over the last couple of years, where the things that we're all excited about is to try and have no hand coding in the pipeline. You can talk philosophically about why we're obsessed with this, but basically the newest models just take the image raw and they try to have as minimal, they call it inductive bias, but I won't define that term, but as minimal kind of information about the model to learn from them. So one weird fact that got me very excited year or two ago was that we have one model for text, and we're using that same model and getting nearly state-of-the-art accuracy on text and images and audio in a bunch of different places. And that is the thing that's really interesting, and it starts from the raw pixels, and it learns the edge detectors and all the stuff we used to do by hand. So that's been the trend. Here we'll talk a little bit more about feature prep, because that stuff doesn't always work, and when it breaks, you want to kind of have a library to fall back on. Wonderful question. But that'll be in, like, I guess, week 4 or 5. Awesome. Please.
What if you can't separate them by a line?
Oh my God, what a great question. Yeah. What if you can't draw this pretty picture? It doesn't make sense. Yeah, that's possible. So what if your features are bad, right? What if it turns out that like your features about cats were like, they sleep on couches? And you're like, well, a dog sometimes sleeps on couches. Then you couldn't possibly separate the dogs and the cats. It's a stupid example, but like your features could be so weak that they're not able to actually separate your class. You could imagine putting a lot more features in, and that's why these models that have bigger and bigger dimensions come in to separate automatically all the different classes. But now your real question is like, okay, there's a fix, but I have my features and I train, what happens? You just make misclassifications, and that's actually the default. You have a small number of features, and then you fit those features, and you do the best you can. So like if a cat jumped over here, there's a cat that was here, you just misclassify it, and you'd get it wrong, right? It'd go from here over to here, and then you'd be toast. So that does happen quite a bit. Sometimes due to label error, and sometimes like there's a subfield of machine learning that is kind of obsessed with this, and my students write papers in it. There's a great benchmark called Wilds from Percy and Chelsea and a couple other folks on the faculty that have these places where machine learning picks out the wrong feature systematically. Like you take a bird that normally is on water and you photograph it with a land background, and the machine learning model is like, oh, that's a land bird, not a water bird. There's a lot of that going on. So that absolutely 100% happens. Wonderful questions. Awesome. Any other questions? All right, so just to recap, what do we do today? We went through this exponential family of models, and now we've hopefully tied in a bow the fact that we had this method to our madness about doing binary and then real valued. We went real valued and binary because you'd seen fitting lines. We did classification, and we tied them all up in these exponential family models. We talked about why inference and learning were basically the same in these models, and that let us generalize to a whole host of them. This is the workhorse of supervised machine learning, but the questions that you're asking now are exactly the right questions. Where do these features come from? What if the features don't fit the data? How do I get more expressive things? You're going to see things about kernels and SVM and neural nets in the next couple of lectures, and that will tell you how do you pick your features and how do you get to these more expressive models, and that will form the bulk of supervised machine learning. Then the next section will come to unsupervised, and we'll forget the whys and figure out what structure can we get there. And that's when we'll get into questions like PCA. We'll get into these questions about what are called exponential family models or EM models, where you have a supervised predictor and an unsupervised thing. And this allows you to do some pretty wild stuff, like fit data from quasars and stuff. And we'll walk through all that stuff. And in fact, we'll also have a thing on self-supervision, which is a new lecture just this time. I guess my student gave it last year, but Tengyu's going to give it this year. Thanks so much for your time and attention. Have a wonderful rest of your week.